Assalamu alaikum wa rahmatullah. Dear students, once again we will go through the exercises for chapter 12. So the first exercise, so we have a pure Aloha network with 100 stations. If the time for each frame is 1 microsecond, what is the number of frames each station can send to achieve the maximum efficiency? Remember, the maximum efficiency is where G, or the load, equals to 1/2. So this maximum efficiency is the actual frames sent over the total capacity. So it's interesting because we have only one number, the frame transmission time, but we know that if if one frame takes 1 microsecond to be sent, how many frames can we send in 1 second? So this is the capacity. So from here we can simply say that the capacity equals to 10 to the power 6 frames per second. So the system now can send a total capacity of 10 to the power 6 frames per second. If that's the case, then total frames sent equals to, of course, 10 to the power 6 divided by 2, or times the G. So the actual frames sent equals to 500,000 frames. Okay, so total frames per station equals to the 500,000 divided by the number of stations, which is 5,000 frames per second per station. So each station can now send 5,000 frames per second. And this is because for maximum efficiency for Aloha, the optimal load is half. So if we want to repeat the same for the slotted Aloha, we know that maximum efficiency is when G equals to 1, which means that the actual frames sent by all stations equals to the total capacity, which is 10 to the power 6 frames per second. So then number of frames sent by each station equals to 10 to the power 6 divided by 100, which is 10,000 frames per second. So this is the number of frames per second that each station can send. Next exercise, we have a CDMA with collision detection network with a data rate of 10 megabits per second. The minimum frame size is 512 bits for the correct operation of the collision detection process. So we know that in order for this to happen, the condition is the time that a frame can take to transmit equals to at least double the propagation time. So what should be the minimum frame size if we increase the data rate to 100 megabits per second, or 1 gigabits per second, or 10 gigabits per second? So basically, we need to know how does the minimum frame size look like proportional to the data rate. So in order to do that, we know that the condition for the minimum frame size is when the frame transmission time equals to double the propagation time. So we know that the propagation time equals to the distance divided by the speed. and the frame transmission time is frame size divided by the total bandwidth. Okay, so then this minimum frame size equals to 2 times the distance divided by the speed times the data rate, or the total bandwidth. Okay, so we know that this frame size equals to 512, so then 512 equals to this amount, which is, we can call it, let's say K, times the actual bandwidth, or 10 times 10 to the power 6. Which means that here, this amount is actually K equals to 512 divided by 10 to the power 7, or in other words 51.2. So the unit of K is not important, but it's actually in seconds, so this is microseconds. Okay, so which means that for 100 megabits per second bandwidth, the minimum frame size equals to K times the total bandwidth. So K is 51.2 times 10 to the power minus 6 times the 100 times 10 to the power 6. So it's 5,120 bits. And of course, for 1 gigabits per second, it's actually 5,1200 bits, and for 10 gigabits per second, it's simply 5,12000 bits, which means that the minimum frame size is directly proportional to the data rate. Okay, so next, here in this figure below, the data rate is 10 megabits per second. The distance between A and C, so this distance is 2000 meter. Okay, and the propagation delay is 2 times 10 to the power 8. As station A starts sending a long frame, so starts from here, sending a long frame from time t1 equals to 0. So this time equals to 0. And station C starts sending after time 2 equals to 3 microseconds. The size of the frame of A and C are long enough to guarantee the detection of collision by both stations. So the question here is asking to find the time when station C hears the collision, or time t3. So basically this time is based on, when we start here, what is the propagation time, or what is the time we take to propagate all the way to C. Given that the distance is 2,000 meter and the speed is this, so we can basically calculate the propagation time, which is simply, so t3 minus t1 equals to the distance divided by 210 times 10 to the power 8, which is 10 microsecond. So this means that t3 equals to t1 plus 10, or in other words 10 microsecond. So this time is 10 microsecond. Okay, so what is the time when station A hears the collision from C? Or in other words, C starts sending at time 3 microsecond, and we need to calculate the time at A. So in other words, t4 minus t2 equals to the same thing, equals to 2000 divided by 2 times 10 to the power 8, which is also 10 microsecond. But here we didn't start from 0, we started from 3 microsecond. So T4 equals to T2 plus 10, which is 13 microseconds. So this time is 13 microseconds. Type C here asks about the number of bits the station C has sent before detecting the collision. So starting from T1 all the way to T4, or in other words, after 13 microseconds, because here T1 is 0. After 13 microseconds, station A sent how many bits? So basically, we know that the transmission, T transmission, or the number of bits, number of bits divided by the bandwidth. So if in 13 microseconds we would have sent number of bits equals to 13 times 10 to the power minus 6 times the bandwidth, which in that case the bandwidth is 10 megabits per second. So 10 times 10 to the power 6, which is 130 bits. And what is the number of bits station C has sent before detecting the collision? So in other words, the T3 minus T2. So remember here T3 is 10 and T2 is, so T3 minus T2 equals to 10 minus 3 equals to 7 microseconds. So how many bits station C has sent before detecting the collision? So basically we calculate the number of bits by multiplying the 7 times 10, or 7 microseconds times 10 to the power minus 7, which in that case is equal to 70 bits. Okay. So the next exercise talks about a network with 1 primary and 4 secondary stations that uses polling. The size of the data frame is 1000 bytes, and the size of the pull, acknowledgement, and negative acknowledgement is 32 bytes each. So each station can send 5 frames to has five frames to send. So here, total number of frames to send equals to 5 frames for each station. So we have 20 frames. So total number of bytes equals to 20 times the size of 1 frame, which is 20,000 bytes. Okay, so we have to account for the pulling and the acknowledgement for each of these frames. So if a station can send only 1 frame at a time as a result of a pull, so the total bytes, remember we have 1 pull plus the frame plus the acknowledgement, because each station can send only 1 frame as a result of a pull. And we have 4 stations, so we have 5 frames, so we have to multiply by 5 for each station, and we have to multiply by all the stations. But remember that this is not all, because we have to at least once send a pull to each station and get negative acknowledgement to mark the end of the transmission. So if this is sent to 4 different stations, so we end up with 4 different pulls and acknowledgement. So this means that the total number of bytes equals to 20 times 32 plus 1000 bytes plus 32 plus 4 times 32 plus 32, which for the negative acknowledgement. So this is equal to 21536 bytes. So the overhead, the total overhead equals to, of course, this total number of bytes minus the 20,000 bytes, or in other words, it's 1536 bytes overhead. So we can divide that by the 20,000 to get this overhead in terms of percentage. Okay, so the next part of this question talks about repeating the same thing, but in that case there's no limit on the number of frames that the station can send as a result of a pull. So pay attention here that the total number of bytes equals to, of course here we have one pull, and then for one pull we can send 5 frames, all the 5 frames we can send until the station stops sending, and then we send the acknowledgement. The station will stop the transmission that it does not have any other data to send. So in that case we need to multiply only by 4 stations, because for each pull we can send all the 5 frames. And then to make sure that the nodes will not have any other frames to send, we need to also send 4 different pull and get negative acknowledgement from the stations. So in other words, the number of bytes equals to 32 plus 5 times 1000 or 5000 plus 32 plus 4 times 32 plus 32. So this is 21024 bytes, or in other words, the overhead equals to only 1024 bytes. So we have around 500 bytes more if we allow the station to send only 1 frame at a time. Last exercise for this chapter talks about a CDMA system with 4 stations 1, 2, 3, and 4, such that station 2 wants to send 1 bit 0 and station 4 wants to send 1 bit, which is 1. Both stations 1 and 3, they are silent. So the first thing is to generate the Walsh table for the chips. So the best way to generate the Walsh table, as we have discussed in class, is to start from Walsh table with dimension 1. So basically Walsh of 1 equals to just -1, and Walsh 2 we can repeat this -1, -1, -1, and then we reverse, in which case Walsh 4 equals to, we repeat this pattern 3 times, so -1, -1, -1, 1, and then -1, -1, -1, 1, and here -1, -1, -1, 1, and here this one we reverse it, so it would be 1, 1, 1, -1. Okay, so this means that station 1 will have this chip sequence, station 2 will have this chip sequence, station 3 will have this chip sequence, station 4 will have this chip sequence. Of course, for station 1 and 3, we don't care because they are silent, so it's 0, but we need this second row. This second row is for station 2 and station 4. Remember, station 2 wants to send 0, and 0 here is, we convert of course 0 to -1. So for station 1, station 1 will send 0, so it would be 0. So station 2 wants to send -1 multiplied by the second row in the Walsh table 4, so it should be 1, and then -1, and then 1, and then -1. Okay, so station 3 is also silent, so it should be 0, or in other words, this one is 1, minus 1, 1, minus 1, and this one is 0, 0, 0, 0. Station 3 is silent, 0, 0, 0, 0. Station 4 wants to send 1, or in other words, minus 1, 1, 1, minus 1. So this should be minus 1, 1, 1, and then minus 1. Okay. So in that case, the composite signal would be, of course, here plus 1. So here plus 1 and minus 1, so the result is 0. And here minus 1 and 1, the result is also 0. And then 1 and 1, so the result is 2. And then minus 1 and minus 1, the result is minus 2. So we have the composite signal would be 0, and then 0, and then plus 2, so it should be like this, and then minus 2. So we know that the code for station 2, if we want to receive the signal for station 2, the code for station 2 is minus 1, 1, and then minus 1, 1, or in other words, so minus 1, 1, minus 1, and then 1. So we multiply each of these with each other, so 0 multiplied by minus 1 is 0, and then 0, and then this one is, and then for this one, 2 multiplied by minus 2 is minus 2, and then minus 2 multiplied by 1 is also minus 2. So here you have minus 2 and minus 2. So in that case, the total is minus 2 plus minus 2 equals to minus 2. And as we know, minus 4 is, if we use an integrator, the minus 4 is definitely bit 0. So this can demonstrate how can we receive station 2 from the composite signal of 2 and 4, while station 1 and station 3 are silent. So that's the end of this part. Thank you very much for listening.